The moon is no longer simply a barren, quiet body drifting through space. Recent revelations from China's exploration of its far side have uncovered something far more perplexing. Hidden beneath its crust lie substances and formations unlike anything ever identified before, challenging many long-held scientific assumptions. But what could these discoveries mean for our future? China's expanding lunar ambitions, while NASA has devoted most of its resources toward Mars missions and advanced telescopes. China has emerged with one of the most carefully structured lunar programs since the Apollo era. Their Chang'e missions, named after the mythical Chinese moon goddess, have advanced step by step in deliberate stages. Chang'e 1 and Chang'e 2 were orbital missions that mapped the moon's surface in extraordinary detail. In 2013, Chang'e 3 carried out the first successful lunar landing since 1976, delivering a lander and rover on the moon's near side. But the real breakthrough came in January 2019, when Chang'e 4 accomplished the unprecedented landing on the moon's far side. Operating there is no easy feat, since direct radio contact with Earth is blocked by the moon itself. China circumvented this by first launching a relay satellite to a stable gravitational point beyond the moon, creating a permanent communications bridge. This ingenious step opened up exploration of terrain humanity had never before seen directly. Its small rover, Yutu-2, Jade Rabbit 2, has been traversing the Von Karman crater inside the massive South Pole Aitken Basin for over 5 years now, well beyond its original 3-month mission plan. Data sent back continues to reshape lunar science, forcing revisions to traditional geological models, and the momentum hasn't slowed. In 2020, the Chang'e 5 mission retrieved lunar samples for the first time since the Soviet missions nearly half a century ago. Unlike the Apollo samples, which came from similar regions on the near side, these were carefully collected from comparatively younger volcanic plains, presenting brand new insights into the moon's evolution. In 2024, China went a step further. Chang'e 6 brought back samples from the moon's far side, something no mission had ever achieved. Laboratories in China are now analyzing these specimens, with initial results pointing to compositions vastly different from those retrieved during earlier space missions. What sets China apart is its systematic long-term strategy. Each mission provides technology and knowledge for the next stage. This effort isn't about symbolic presence or planting flags, it's about locating resources, testing ways to process them, and building capacity for the International Lunar Research Station, a permanent base projected to be completed before 2035. The designs are already prepared, prototype systems are being tested, and progress continues steadily, even as NASA's Artemis program grapples with funding and delays. Strange substance on the far side. One of the earliest and most intriguing surprises came in 2019, while Yutu-2 was exploring a small crater on the lunar far side. Its cameras picked up something highly unusual, a material with an odd, shiny texture and a greenish tint, starkly different from the surrounding dust and rocks. At first, scientists described it as a gel-like substance that reflected light in peculiar ways. The find quickly sparked speculation across the globe. Some observers thought it could simply be melted glass from meteorite strikes. Others suggested volcanic residue. A few even posed more exotic theories, though ideas of biological origin were quickly dismissed. Subsequent analysis using the rover's onboard spectrometers pointed toward a likely explanation: impact melt breccia, a dark, glassy material formed when the tremendous energy of meteor impacts melts and fuses rock together before cooling. Think of it as nature's version of forging glass by smashing diverse materials with extreme heat and pressure. Still, there was something puzzling. The patch, measuring roughly 20 inches by 6 inches, displayed properties suggesting either unusually recent formation or a more complex melting process than models had predicted. What made this so strange was the context. The moon's far side has a thicker crust and fewer radioactive heat sources, which should reduce the likelihood of fresh melt glass forming in such regions. This raises key questions. What process could have created this substance so recently? Is there still hidden geologic activity occurring on the moon's far side? The mystery remains unresolved. The glass sphere enigma, and the story didn't end there. After uncovering the mysterious gel, U-22 stumbled upon something even more enigmatic: perfectly rounded glass-like spheres scattered across the far side surface. These discoveries have left scientists debating possibilities, suggesting the moon may be far more geologically active and dynamic than previously assumed. As China's U-22 rover continued its unprecedented trek across the lunar far side, it stumbled upon a discovery that looked more like something crafted for a science fiction film than a natural formation. Scattered across the dusty, gray surface were smooth, translucent glass spheres sparkling faintly in the sunlight. These weren't dust-sized fragments or sand-like beads. They measured between half an inch and nearly a full inch across, far larger and clearer than the microscopic glass particles that Apollo astronauts once brought back. Until this find, nothing of that size or purity had ever been recorded on the moon. Scientists have posed two leading explanations for these orbs. One idea suggests they were forged in the chaos of meteoroid strikes. The immense force and heat from such impacts could have melted chunks of anorthosite rock, which then cooled into perfectly rounded glass. The second possibility is that they originated in the moon's ancient volcanic era. Billions of years ago, eruptions may have sent molten material spraying skyward in fiery fountains, later falling back as glowing droplets that solidified into neat, spherical forms, a process not unlike what happens with lava showers on Earth. Yet despite these hypotheses, the glass spheres remain a mystery. Their unusually large size, flawless roundness, and striking clarity exceed what we'd expect from either meteoritic impacts or volcanic sprays. The sheer amount of energy needed to create orbs of this scale appears far greater than what conventional lunar processes should provide. Stranger still, the spheres are not scattered randomly. Instead, they seem to lie in patterns with geometric regularity, almost as though shaped by forces below the surface we don't yet understand. Could unknown pressure dynamics or geological mechanisms be arranging them? Or, more profoundly, are we seeing signs of processes not accounted for in existing planetary science? Whatever their origin, these glass globes represent one of the most puzzling findings on the far side, preserved in silence for billions of years. They may contain hidden records of the moon's interior systems, waiting to reshape our understanding of its evolution. The South Pole Aitken Basin, a gateway into the moon's interior to understand why China's recent missions are so groundbreaking. It's critical to look at where they've focused their exploration. Both Chang'e 4 and Chang'e 6 deliberately targeted the South Pole Aitken Basin, a vast scar on the far side of the moon. This is no ordinary crater. At roughly 1,600 miles across, it ranks as one of the largest impact structures in the entire solar system. Scientists believe it was carved more than 4 billion years ago, when an asteroid, possibly the size of a small state like New Jersey, slammed into the moon with unimaginable force. The collision was so violent that it likely ruptured the crust completely, exposing deeper layers of the mantle beneath. Think of it like smashing an eggshell. The outer surface cracks open, giving you a glimpse of what's hidden inside. That makes the South Pole Aitken Basin the best natural window into the moon's inner layers. A chance to study material normally locked dozens of miles underground. Data from Chang'e 4's instruments indeed found something extraordinary: rocks unusually rich in low-calcium pyroxene and olivine. These minerals are considered hallmarks of mantle composition. The quantities observed weren't just trace signatures. They appeared in concentrations strong enough to suggest they truly originated from the moon's interior. This was revolutionary, because no previous mission, not Apollo, nor Soviet lunar samples, had ever provided such direct mantle evidence. And in 2024, Chang'e 6 built upon the finding by physically returning far-side samples to Earth for the first time. Detailed study confirmed the earlier data. These rocks contain mineral makeups consistent with material from deep beneath the lunar crust. This discovery effectively settled a heated scientific debate. The South Pole Aitken impact was indeed catastrophic enough to penetrate the protective outer shell and dredge up ancient mantle fragments. In other words, China's missions have handed researchers a geological time capsule, preserving pieces of the moon's interior chemistry since its earliest formation. But these findings go beyond simple curiosity. They raise unsettling questions that strike at the core of our models about the moon's makeup. The chemical profile of the mantle samples retrieved doesn't line up with long-standing theories. The ratios of key elements are noticeably off from what scientists expected. This leaves two possibilities. Either our entire understanding of the moon's internal structure is fundamentally flawed, or unknown processes have altered these materials in ways we still can't explain. Evidence of volcanism, where none should exist. The Chang'e missions weren't limited to collecting surface rocks. They carried something none of the Apollo astronauts had: ground-penetrating radar, capable of scanning below the regolith. When U-2 deployed this technology inside the von Karman crater, the results upended everything we thought we knew. Beneath the crater floor, the radar mapped layer after layer of buried volcanic basalt, stacked deep into the subsurface. This was unmistakable evidence of repeated lava flows stretching hundreds of meters downward. And the pattern wasn't random. The older, deeper flows were far thicker than the upper ones, suggesting an early period of intense volcanic eruptions that slowly diminished, exactly what you'd expect from a body cooling across geological time. But there's a glaring paradox. This should not be possible on the moon's far side. For half a century, scientists believed the far side's crust was simply too thick for magma to reach the surface. Adding to the puzzle, that hemisphere doesn't contain high concentrations of radioactive elements like potassium, thorium, and phosphorus, materials that generate the internal heat necessary to power long-lasting volcanism. Based on accepted models, the far side should have gone geologically dormant billions of years earlier than the near side. So why do the radar scans reveal a history of persistent eruptions? Some researchers suggest that the South Pole, Aitken impact, may hold the key. The collision was so catastrophic that it could have fractured the crust all the way down to the moon's interior, creating channels for magma to seep to the surface. Others hypothesize there may be undiscovered reserves of radioactive materials deep below the far side that never registered on orbital scans. Either scenario hints at hidden processes shaping the moon in ways current planetary science hasn't accounted for. A new lunar mineral, Chang'e-Y. Then came another revelation in 2022, announced by Chinese researchers after examining samples brought back by Chang'e. Among the fine lunar dust, they identified an entirely new mineral, dubbed Chang'e-Y, a phosphate crystal never before seen in Earth laboratories or earlier lunar samples. Though just 10 microns across, smaller than a red blood cell, its implications are vast. The mineral was forged in the searing chaos of an asteroid impact, inside a molten pool of rock that solidified under intense pressure. Simulations suggest such conditions would require a crater at least 2 to 20 miles across. What makes Chang'e-Y especially significant, however, is not just its rarity, but its composition. Inside its crystal lattice were atoms of helium-3, a virtually absent resource on Earth, but believed to exist in abundance across the lunar surface. This wasn't just a scientific trophy. It was a potential strategic breakthrough. Chang'e-Y was extracted from the youngest volcanic samples ever recovered, basalts that erupted only about 2 billion years ago. Much younger than any Apollo specimens. That means there may be far more of this mineral, and others like it, scattered in lunar regions older missions never explored. The energy of the future? The real shock wasn't the mineral itself, but the helium-3 it contains. For decades, futurists and energy researchers have pointed to helium-3 as perhaps the most valuable substance in the solar system. Earth has virtually none, but the moon has been bombarded unfiltered by solar winds for billions of years, embedding helium-3 into its surface regolith. The reason helium-3 matters comes down to nuclear fusion. Unlike today's fission reactors, which create dangerous radioactive waste, a helium-3 based fusion reactor could conceivably produce vast amounts of clean energy with negligible byproducts. In theoretical terms, just 1 metric ton of helium-3 could generate as much energy as 10 million tons of coal. In short, this isn't just a curiosity for scientists. It could be the fuel of the future, a resource able to transform not only space exploration, but Earth's entire energy landscape. And the moon, particularly the regions China has begun probing, might be the largest accessible reservoir in the solar system. Helium-3, the lunar energy goldmine. China's study of the samples returned by Chang'e provided the world's first direct measurement of helium-3 levels in lunar soil. While the precise figures remain undisclosed, The results confirmed long-standing theories. The moon contains substantial, extractable reserves of this nearly priceless isotope. The implications are staggering. Experts estimate that the lunar regolith could hold over 1 million tons of helium-3 if harvested and transported back to Earth. Such reserves could theoretically meet humanity's energy needs for hundreds of years. Chinese researchers have noted that the amount of helium-3 carried by the equivalent of just 3 space shuttle loads could power the entire planet for 1 year, if fusion technology is perfected. But here's the challenge: extracting helium-3 would demand industrial-scale mining operations on the lunar surface. Roughly 150 tons of soil must be processed to secure a single gram of helium-3. That means large-scale excavation facilities, refineries, processing centers, and crucially, a permanent human presence on the moon. This explains the urgency behind China's lunar strategy. The nation that secures access to helium-3 could effectively control the future of global energy, with the isotope valued at tens of thousands of dollars per gram in terrestrial markets. The economic and geopolitical implications are almost beyond imagination. Water on the moon, a turning point even more surprising than helium-3. However, were China's findings regarding lunar water. For decades after Apollo, the moon was assumed to be bone dry. That belief was shattered when the Chang'e 5 lander returned the first on-site detection of water on the sunlit surface. Using spectrometers, the lander measured up to 120 parts per million, ppm, of water in the regolith. And one rock sample recorded an even higher value of 180 ppm. While these numbers equate to less than 0.02% by weight, their significance is enormous. It proved water exists even in regions exposed to intense solar radiation. The revelations didn't stop there. When Chang'e 5 scientists studied the tiny glass beads within the lunar soil, formed by micrometeorite impacts, they discovered these spheres contain water trapped inside their structure. In some cases, concentrations reach 2,000 ppm, 0.2% by weight. This wasn't contamination, but rather a natural capture process. When meteorites hit, the heat melts the soil into glass. As the molten glass cools, it absorbs hydrogen atoms from a solar wind, which later bind with oxygen to create water molecules locked within. The true importance lies in the sheer abundance of these glass beads. They are everywhere, in every sample, scattered throughout the upper layers of the regolith. Collectively, they may hold billions of tons of water across the lunar surface. And unlike the ice frozen in permanently shadowed polar craters, these resources are spread globally, meaning water could, in theory, be extracted almost anywhere on the moon for future colonies. This is a game changer. Water isn't just essential for drinking, it can be split into oxygen and hydrogen, providing breathable air and powerful rocket fuel. This means tomorrow's lunar bases won't be confined to the treacherous darkness of polar craters. Instead, astronauts could mine water molecules almost anywhere by heating regolith. The second space race, these discoveries have exploded beyond the realm of science, reshaping global strategy and geopolitics. Experts now openly call it the new space race. The United States views China's progress with rising concern. In 2024, NASA Administrator Bill Nelson made headlines when asked during a congressional hearing if the U.S. is locked in a race against China for resource-rich regions of the lunar South Pole. His answer: yes, I do think we're in a space race. Nelson warned that if China establishes dominance at the moon's South Pole, it might attempt to claim territory and resources, comparing the potential situation to China's territorial maneuvers in the South China Sea. He added bluntly, I do think there's a military aspect to what China is doing in space. This was the first time NASA had so openly tied lunar exploration to geostrategic rivalry. At the heart of this contest lie the moon's permanently shadowed polar craters, rich in ice, and regions dense with helium-3 deposits. These aren't just scientific curios, they are strategic assets that could decide which nation is capable of sustaining a permanent presence in space. China has already set ambitious plans in motion. Its International Lunar Research Station, ILRS, intended to be established near the South Pole by the early 2030s, will be much more than a scientific outpost. Blueprints call for power generation facilities, mining and resource extraction installations, and eventually, permanent human habitation. The timeline is accelerating. Chang'e 7, slated for launch around 2026, is designed to land near the South Pole with a hopping microlander to directly explore shadowed craters for ice. Chang'e 8 will follow, testing technologies for in-situ resource utilization, effectively a rehearsal for building sustainable bases. China's strategic edge, what most worries U.S. policymakers, is the methodical nature of China's lunar strategy. While NASA's Artemis program has endured delays and shifting budgets, China's missions have advanced with consistency, guided by a clear long-term vision. It isn't simply exploration for prestige. Beijing is mapping resource deposits, testing in-situ extraction, and building the framework for industrial operations on the moon. The stakes couldn't be higher. The nation that first develops a sustainable presence on the lunar surface will gain advantages that extend far beyond. Science, water ice, once melted, can be broken into hydrogen and oxygen for rocket fuel, life support, and radiation shielding. Meanwhile, helium-3 could become the foundation of fusion power, providing clean energy on Earth and beyond resources. The moon itself represents the ultimate strategic high ground, a platform to control cislunar space, and potentially access to deeper planetary orbits. Former U.S. Air Force Secretary Heather Wilson summed it up in stark terms. The country that establishes the first permanent lunar base will set the rules for space development. Just as Britain's naval dominance in the 19th century allowed it to shape international maritime law. What Apollo missed to understand why these new findings are revolutionary. We need to revisit the limitations of Apollo. From 1969 to 1972, NASA landed astronauts 6 times on the moon, all on the near side, all within a narrow band close to the lunar equator. The northernmost Apollo landing only reached 26 degrees latitude, and the southernmost just 9 degrees. On Earth, that would be the equivalent of exploring only between Miami and Dallas, leaving out the Arctic, the Antarctic, and nearly every continent. Apollo astronauts collected an impressive 842 pounds of samples, but all came from similar volcanic plains and equatorial terrain. They never explored the polar regions, the highlands in depth, nor the far side that always faces away from Earth. In essence, half the moon, an entire hemisphere, remained completely untouched until China arrived. This is why the Chang'e program represents such a dramatic leap forward. Chang'e 4 became the first mission in history to land and operate on the far side. Chang'e 5 brought back the first moon rocks in more than 4 decades, targeting geologically young volcanic fields far removed from Apollo sites. And most recently, Chang'e 6 achieved something even greater, the first ever sample return from the far side. Through these efforts, the stark differences between the two hemispheres are becoming clearer. The near side is dominated by broad, dark basaltic plains called Maria, formed by ancient volcanic eruptions. Its crust is relatively thin, averaging 37 miles, and rich in radioactive elements like potassium, rare earths, and phosphorus, together known as KREP. By contrast, the far side is a rugged, heavily cratered highland with crust measuring up to 50 miles thick, virtually no large Maria, and far fewer radioactive heat-producing elements. The crown jewel is the South Pole Aitken Basin, the largest and oldest impact scar on the moon, where China focused exploration. This basin likely punched deep enough to expose mantle materials from dozens of miles beneath the crust. The asymmetry between hemispheres, near side versus far side, has baffled scientists for decades. Why would a single planetary body evolve in such dramatically different ways? Thanks to China's missions, we now have tantalizing clues: mantle minerals on the surface, buried layers of ancient lava flows, and far-side basalts offering a geological story unlike anything Apollo ever revealed. The new lunar future taken together. China's discoveries are not merely rewriting textbooks, they are laying the foundation for a new lunar age. The strange gel-like materials, translucent glass spheres, far-side mantle rocks, and water-rich glass beads all fit into a growing puzzle. The implications ripple outward across science, technology, and geopolitics. Energy security, helium-3 in the lunar regolith hints at a future powered by clean, Radiation-free fusion energy, perhaps solving Earth's energy crisis for generations. Even though helium-free fusion reactors remain experimental. The verified presence of the isotope has already accelerated research worldwide. Habitat sustainability. Water isn't just vital for survival. It's fuel, breathable oxygen, and protection against solar radiation. Knowing that water is far more widespread than once assumed brings lunar bases within reach at many more sites, not just the frozen polar shadows. Origins of the Earth-Moon system. The far side discoveries challenge our models of how the Moon, and by extension, Earth formed. Mantle materials exposed by the South Pole, Aitken Basin provide a rare window into the violent early history of the solar system. What is emerging now is the reality that the Moon is no longer just a silent, dusty rock. It is a strategic frontier, a resource vault, and humanity's first stepping stone toward permanent habitation beyond Earth. For the first time in 6 decades, the global race is not led by the United States. It is China that has achieved milestone after milestone. The first far-side landing, the first plant grown on the Moon, the first lunar samples returned in more than 40 years, and the first far-side samples brought back to Earth. Beijing's International Lunar Research Station, ILRS, is moving forward with precision. Each mission builds directly on the last, pushing toward permanent infrastructure and, eventually, large-scale human habitation before 2035. Unlike Apollo, this strategy is not about planting flags. It's about establishing permanence. We now stand at a crossroads. The Moon, once dismissed as lifeless dust, is emerging as a complex, resource-rich world of critical importance to science, survival, and power. The discoveries unfolding today are not just defining our understanding of the Moon, they are defining the future of humanity's place in the solar system.